exponential functions and logarithmic functions. In this video, we are going to graph exponential functions and analyze them. So this red graph here is our typical exponential function of the form of y equals a to the power of x, where a is some number that's larger than 1. If you have a base of 1 over a, so a proper fraction, then we have a decreasing function, which is the gray one indicated on the graph. So when a is greater than 1, as x increases, y increases. So the function is increasing when your base is larger than 1. If your a value is a proper fraction between 0 and 1, this means that x decreases and y decreases as it approaches 0, so the function is decreasing. Here are some characteristics I want you to remember about exponential functions. A graph has an y-intercept of 1, and that is true for any basic graph with no transformations acted upon it, or translations. And the graph will approach the x-axis but never reach it, and that is for y equals a to the power of x, or y equals 1 over a to the power of x. So there's a horizontal asymptote with an equation of y equals 0. This graph does not have an x-intercept because it doesn't cross the x-axis. The domain of the function is from negative infinity to positive infinity, or x is the element of the reals, and the range of the function is y is greater than 0, or from 0 to infinity. So let's graph y equals 3 to the power of x. Before I even begin to graph this, we know this function is increasing because 3 is a number that is larger than 1. And then I'm going to use a table of values to help me determine a few points. So I'm just going to pick -1, 0, and 1. And I'll plug it into 3 to the power of x. So this will be 3 to the power of -1, which is a third, 3 to the power of 0, which is 1, and 3 to the power of 1, which is 3. I'm going to go ahead and draw in my x and y axis, label it, and draw in the corresponding points. And the shape should be the same shape as the red graph from above here. So I'm going to follow the similar shape to that. And I'm going to make sure that on the left-hand side, for my end behavior, is approaching an horizontal asymptote of y equals 0. I'm also going to draw in that asymptote there. So this is our graph of y equals 3 to the power of x. Now I need to describe the intercepts, the asymptotes, domain, and range. So your y-intercept is just located at 1. Your asymptote is a horizontal line located at y equals 0. Your domain is from negative infinity to positive infinity, and your range is from 0, remember it's a round bracket because we don't touch 0, up to infinity. So I want you to go ahead and do the next question on your own. In this case, our base is 1 over 3, which means this is a decreasing function now. Use the same method as I have used, using a table of values to find a few points, and then graph it, following the same shape for exponential functions, and then find some characteristics of it after. When you're ready, press play. So here's the solution to the try it yourself. I found 3 points using x equals -1, 0, and 1 in a table of values to find its corresponding y value. And then I graph those points on an xy plane. You can clearly see it's a decreasing function, and we again should know it's decreasing because a is a third, which is smaller than 1. It's a proper fraction. Your y-intercept is at 1, your asymptote is at y equals 0, domain is from negative infinity to positive infinity, and your range is from 0 to infinity. Now we're going to look at transformations of exponential functions. And it takes on this form. You could also use this form as well. So C is a vertical stretch. D is a horizontal stretch or compression. This H will determine your translation from left to right. And I'm going to move the K over to the other side, and this will give you your translation for up and down. So here's a brief description of what I just said. So K again, translate the graph up or down. C stretches the graph vertically. It also can reflect the graph in the x-axis if you have a negative. D stretches the graph horizontally by 1 over D and reflects the graph in the y-axis if D is negative. And lastly, H translates the graph from left to right. So here are your steps. The first thing you're going to do is rewrite it in the form of y equals, and again you can move this K to this side. So it would be C a to the power of D multiplied by x minus h plus k. So you should determine any translation and stretches, and note that stretches will be approximate when drawing. They don't have to be perfect, but if you just find 2 to 3 points, that would be enough to show its shape. If there's a vertical translation, then you should draw in that horizontal asymptote. So for example, if you're going to move the graph up 2, then your horizontal asymptote will be at y equals 2. Then you're going to determine if there are any reflections, and that is if C or D is negative, and that's when you're going to know you're going to have some reflections. We're going to use the point 0, 1 as a reference and find its translated point, just like in Unit 3 when we did transformations. Then graph the point with its label, and then draw the correct directions for the arms according to its reflections. You could also use the table values method that I've used in the previous 2 examples. So let's go ahead and try an example of this. This is a graph that we're going to draw. 2 to the power of 2x minus 4. And we want to know if this function is increasing or decreasing. Right away, we should know this function is increasing because we have a positive a value that's larger than 1. So since our base a is 2, which is greater than 1, the function is increasing. Take a note that this may not always be true if you have a negative in front of the 2 to the power of 2x, because you have to reflect, and that could make your overall graph be a decreasing function. The next thing I'm going to do is use a table of values. So I'm going to go ahead and use x equals 0, and the other point can just be 1. So then we have 2 to the power of 0 minus 4. 2 to the power of 0 is 1, and then 1 minus 4 is negative 3. For our next point, we have 2 to the power of 2 minus 4. 4 minus 4 is 0, so those are our 2 points. So I'm going to draw and label our xy plane, and then go ahead and graph those 2 points. We know it's an increasing function, so the shape should look something like this. And don't forget to draw in your horizontal asymptote. So usually it's going to be at y equals 0, but because we go down 4, our new horizontal asymptote is going to be at y equals 4, negative 4. So that is your graph. Now we're going to determine its characteristics. So for your intercepts, we actually have an x-intercept this time just because we translated the graph down. So our x-intercept is located at 1. Our y-intercept is located at negative 3. Your asymptote is located at y equals negative 4, and then your domain and range. So your domain is negative infinity to positive infinity. Your range, your lowest end point here in your y values is from -4 and then goes on to infinity. I would like you to try the next one on your own. Be careful because we do need to reflect in the y-axis because there's a negative in front of your x. So go ahead and try this on your own. When you're ready, press play for the full solution. So here is the solution for this try it yourself. I do have to rewrite this before we even start anything because this x in the exponent needs to be factored out. And if you look back to our format for transformations on the second page of your notes, we did say, or it does say, that we have to factor out our value horizontally. So in this case, I'm factoring out a -1. And I'm doing this because this also means that if I ever need to describe how my function is changing, I can see from here that we are moving 2 to the right. And if I didn't factor that out, you might have said to the left, which would be incorrect. Okay, so I'm going to go ahead and find a few points. We can start with y equals 0. We can do -1 and 1 just to be sure we understand what the shape of this graph looks like. So if I plugged in 0, we're going to get 2 to the power of 2, which is 3 times 4, and that's 12. Next, I'm going to plug in -1. Which would be -3 times -1, which is positive 3. That's 3 times 8, which is 24. Then for x equals 1, it's going to be -1 times -1, which is positive 1. 3 times 2 is 6. And we can even do one more to see if we get an even smaller y value. So I'm going to choose x equals -2 as another point that we could try to find. That's 3 times 2 to the power of 0, which is 3. So I'm going to go ahead and now draw in my x and y axis, and I'll label them. Then I'll draw in my corresponding points. And follow the shape of an exponential from left to right. So notice in my right end behavior, we are still going to approach y equals 0 because there is no vertical translation. So our asymptote is still at y equals 0. And then we have a y-intercept at 12. There is no x-intercept. This is a decreasing function. So this is the example where your base has a value that's larger than 1 and it's positive, but we had a reflection in the y-axis which changed our function so that it's actually decreasing. Then your domain is from -infinity to positive infinity, and lastly your range is from 0 to infinity. Moving on to the next example, this is a word problem. The function's already given to us as 7 times 2 to the power of t. So here's our situation. The growth of the internet can be measured by the number of computers offering information. These are called hosts. In 1995, there were about 7.4 million hosts. The number of hosts, n in million, at any time t years after 1995 can be modeled by the function n equals 7 times 2 to the power of t. Now we want to graph the function for 0 to 4. So I'm going to do a table of values on the side, starting from 0 and going up to 4. And remember that t is going to actually be your x, and your y is going to be n, which is the number of hosts, so you can change your variables accordingly. So this is actually t, and this is n. So I'm going to go ahead and plug this into our function to find its y value. So 7 times 2 to the power of 0 is 7 times 1, which is 7. For x equals 1 or t equals 1, this is 7 times 2, which is 14. Then 7 times 2 to the power of 2, which is 7 times 4, and that's 28. Our next one is 7 times 2 to the power of 3, which is 7 times 8, and that's 56. And lastly, 7 times 2 to the power of 4, which is 7 times 16. This is equal to 112. Now I'm going to go ahead and draw in my x and y axes and label it accordingly so I can graph those points. And I'll just go up by 7s here for n. All right, so our first point's at 0, 7, then we have a point at 114, 228, 356, and our fourth point's going to go outside of the grid, so I'm just going to graph it somewhere up here. Then we'll connect our points from left to right. So that's what our graph looks like. Next, it says to the nearest million, calculate the number of hosts in 2010. Well, our t, if you read the question again, is the years after 1995. So we need to first calculate the amount of years after 1995 from 2010. So that's 2010 minus 1995, which is 15 years. So from 1995 to 2010, 15 years have gone by. This is going to be our t. We're going to put this into our function. So 7 times 2 to the power of 15. We're going to get 229,376. And notice that n is a value in million. So this will be 229,376 million. And our last question, in which year did the number of hosts reach 56? We can just either use our table of values or the graph, and we can see this has occurred after 3 years. We want to know which year. So starting from 1995 and 3 years after that is going to be 1998. So that is the year that the number of hosts reached 56. For this last question is a try it yourself question. So go ahead and do this on your own. You might be able to use a calculator for this type of question just because your value is a decimal number, your a value. So you can use a calculator for this for now to find your table of values, then graph those points only from 0 to 5. Then use your graph and the function to find B and C. So go ahead and do that, and then when you're ready, press play for the full solution. So here's the graph to the chart yourself. I did table values on the side from d equals 0 to 5, and I got p-values from that. And I graphed that right onto the grid. That one's pretty self-explanatory. Then for B, to find the nearest percent, how much light remains at a depth of 10 meters. So we're trying to find P, and then we're going to insert our depth of 10 meters into here, put in the calculator, and you're going to get about 0.1%. Remember, P is the light remaining in percent. Then for C, to the nearest meter, what is the depth? So we're looking for D when only about 6% of the light remains. So we're looking for D, we're given P. You're going to look at your graph or your table values to figure out what depth we're going to achieve this at, and it looks like it's going to be about 4 meters, and according to our information it would have been about 6.25%, but it did say about 6%, so it's okay to say 4 meters.